Hello, my name is Koki Honda from Keio University. I'm talk about CLAHE implementation on a low-end FPGA board by high-level synthesis. Recently, car maker replacing side mirror with camera. As a result, applying image processing on the camera image became possible. Our focusing application CLAHE is the candidate of it. CLAHE is used to improve image quality. It can be used to improve dark image of the side mirror camera. But low-end embedded CPU can't satisfy time requirement. So we implement CLAHE on a low-end FPGA. CLAHE has two main processing parts: cumulative histogram function generation and interpolation. First, at step 1, image partitioned to subtiles, and the CDF is generated from each tile. After that, at step 2, each pixel is converted by bilinear interpolation using adjacent tiled CDF. Before explaining implementation, we provide several background information. Our target board is Pink Z1 board. It is low-end Zinc 7000 board, and it has dual-core ARM Cortex-A9 and RTX 7 family FPGA. We used Vivado 2019.1 and Vivado HLS 2090.1. As time requirement, to use on vehicle, 30 FPS is required. In terms of computational complexity, CDF generation is order n, and interpolation is order n. So, CLAHE's computational complexity is order n. Next, we'll talk about implementation. Our module consists of 4 submodules: pixel input module, CDF generation module, interpolation module, and pixel output module. Pixel input module partitioned pixels by tiles. CDF generation module creates CDFs from each tile. And interpolation module interpolate pixel using CDF. Finally, pixel output module ejecting converted pixel. In CDF generation module, we place multiple PEs. The number of PE is the number of horizontal tile divisions. One PE handles generating CDF from one tile. Considering the pixel input order, the operating rate of each PE is not 100%. In histogram create loop, we can set loop interval 1. Because our target low-end FPGA cannot meet target frequency. So we set loop interval 2. But our structure mitigates this effect because the processing can proceed parallel. Next, interpolation. To reduce latency, it is important to start the interpolation as soon as possible. To do that, we prepared 3 buffers and revised a calculation method according to the procedure shown in the figure. This figure shows how to process pixels from line n to line n plus 4 of tiles. Each buffer holds the CDF for one row of tiles. The 2 buffer is used to interpolate pixels. Meanwhile, the remaining buffer will be assigned the subsequent CDF. As a result, the interpolation module can start processing without waiting for the CDF of all tiles to be completed. This is the comparison of related research. The lower bound is calculated by the clock period times number of pixels. In fact, the execution time will be longer than the lower bound, because pixels cannot be interpolated until at least one CDF is created. In Full HD image, our work performs fast than related work, and time requirement 30 FPS may be satisfied. We compare our work with Cortex-A9 on the target board and Jetson Nano. This FPGA execution time includes data transfer time between DRAM and FPGA. The purple bar is our work. Also, our design is faster than Cortex-A9. Compared to Jetson Nano's CPU and GPU, the execution time is slower. CLAHE is not a very data-intensive processing, so it has large data transfer time overhead. However, data transfer overhead can be reduced in cases where multiple processing are performed on the FPGA. This is power consumption comparison. The result shows pink Z1 is energy saving. Furthermore, the power consumption of the FPGA alone is much less than 1 watt. Next, resource utilization. This figure shows scalability for image size is limited by VRAM capacity. Other resources are insensitive to change in image size. Conclusion. We talked about the design of CLAHE. In CDF generation, by arranging multiple PEs, the effect of increasing the loop interval was reduced. In interpolation, latency and VRAM usage have been reduced by revising how to follow the CDF and how to calculate. As a result of this technique, we were able to achieve almost the same performance as the HDL implementation by high-level synthesis. Thank you.